In this video, we're going to go through the solutions to every question to the UKMT Senior Maths Challenge from 2022. That's the hardest of the main maths challenges in the UK, usually sat by students aged 16 to 18, often also taken by younger students as well. And if you're preparing for that challenge, do also take a look at my free course, Get Ready for the Senior Maths Challenge. In that course, you can practice all of these questions, as well as questions from other papers, and each one has a video hint and a full video solution. So you can have a go at the question, you can watch the hint if you're stuck, you can really have the best chance of getting the answer by yourself, you can see if it's right and then watch the video solution. It's a really great way to prepare for the Senior Maths Challenge. And over at that courses website, I've got loads more courses to prepare for maths challenges and for school maths as well, so I really hope you will take a look over there. But if you'd like to watch these solutions here on YouTube instead, I will get on with them now. I'll put timestamps below so you can jump to the questions you need if you are working through the paper like that, or if you want to work through the whole paper with me, we can start together here at question 1 and you can pause the video at the start of each solution. So the strong hint in this question is that we want to use the difference of two squares formula. We can see difference of two squares expressions all over the numerator here. Remember, that tells us that a squared minus b squared equals a plus b times a minus b, and of course 1 squared is just 1, so 2 squared minus 1 squared here I can replace with 2 plus 1 times 2 minus 1. 3 squared minus 1 squared would be 3 plus 1 times 3 minus 1, and so on. And if I just write those out, then 2 plus 1 is 3, 2 minus 1 is 1, so this is 3 times 1, and then this would be 3 plus 1 times 3 minus 1, so that's 4 times 2. Then the next one, 4 squared minus 1 would be 5 times 3, and so on. 5 squared minus 1 would be 6 times 4. And now I can cancel terms in the numerator and the denominator. So I've got a 3 that cancels. Don't need to worry about the 1. I've got a 2 that cancels, a 4 that cancels, a 5 that cancels, a 3 that cancels here, a 6 that cancels here, and a 4 that cancels here, and the only thing that I'm left that doesn't cancel is a 5 on the bottom here, and so overall the expression just simplifies down to 1/5, and the answer here is D 1/5. Of course, you could just work these numbers out here, none of them are very big. 5 squared minus 1 is only 24, and you could cancel factors that way, but clearly there's a hint there to use the difference of two squares. That's something that comes up a lot in the Senior Maths Challenge. What's the smallest prime, which is the sum of 5 different primes? This is the sort of question that we're meant to do by a bit of trial and error, really. We're looking for the smallest case, and none of the answers here are enormous when you think about when you add 5 prime numbers together, you're going to get something of this sort of size. Even if I start with the smallest prime numbers, 2 plus 3 plus 5 plus 7 plus 11, if I add those together, I'm going to get 28. Now, you see here that's not in the list, it's too small, but also you see that if we include 2 in the list, we could never end up with a prime result here, because I'd have 4 odd numbers to add together with this even number 2, and that's going to give me an even number, and so that's never going to be prime. So actually I can exclude 2 from the consideration, and then the next one I would try would be 3 plus 5 plus 7 plus 11 plus 13 here. So I'm going to get 11 more than I did in my previous attempt here, so that's going to be 39. That is in the list here. Might be tempted to go for that, but 39 is not prime because it's 3 times 13, so we need to keep searching. So I'm going to have to include the next prime in the list, which is 17. To keep the total as small as possible, I want to try replacing the 13 with 17, and that gives me 43, and 43 is prime. We only need to check here 2, 3, and 5 are not factors for any 2-digit number. Remember, it's prime if 2, 3, 5, and 7 are not factors. We've only ever got to check up to the square root of the number and just prime numbers. So 43 is prime, and it's the smallest number we can get in that way. Of course, these questions are easier when the answers are relatively small. I could keep searching until I find the right answer, and I'm really guided here by the fact that the largest answer was only 53 out of the possibilities. I'm pretty confident at the outset there that that trial and error method is going to be successful quickly enough that it's a good strategy. We want to know how many parallelograms we can find in this figure, and The only way you can get a parallelogram is by putting two of these triangles together, the hexagon splitting into 6 identical equilateral triangles here. And once I've got that one, I can say, well, I can also rotate this into the 6 possible positions. So there's also another one here, another one here, and I can just keep rotating round until I've got all 6 of them here, and the answer here then is 6. You can keep looking for parallelograms, but you won't find any more than that. So here we've got 2 symmetrically placed squares with side lengths 2 and 5. We want to know what the ratio of the area of the small square is to the shaded region. Well, if the small square has side length 2, then clearly the area of that small square is 4, and so I just need to work out the area of the shaded region. Well, if I split the small square into 2 parts here, I've got that would be 2 and 2. Similarly with the large square, that would be 25, so the 2 halves would be 12.5 and 12.5. So this part here would be 12.5 minus 2, which is 10.5. And so the ratio that we're looking for here is the area of the small square 4 to the area of the shaded region 10.5. And now I just need to multiply that ratio by 2 to find that the answer here is 8/21, and so the answer is D. To get this question right, we just need to group the fractions in the appropriate way. So 1 over 1.01 plus 1 over 101. Well, 1 over 1.01 times top and bottom by 100 would give me 100 over 101 plus 1 over 101. Then that's 101 over 101, which is 1. So those two together give us exactly 1. And then 1 over 1.1 plus 1 over 11, in the same way that's 10 over 11 plus 1 over 11, which is 11 over 11, which is also 1. And of course 1 over 1 is also 1, so I've got 1 plus 1 plus 1, and the answer here is C3. Indices is a very important topic for the Senior Maths Challenge, comes up a lot and in lots of different ways. That's why it's one of the central topics of the Go for Gold courses that I've made. A key tactic is to look at the indices you've got and see if they've got a common base. So here we've got 4 and 8 as the bases, but they are both powers of 2. So 4 is 2 squared and 8 is 2 cubed. That's really the key way into this problem. So 4 to the 800 then is 2 squared to the 800, and using the rules of indices, that's 2 to the 1600, whereas 8 to the 400, that's going to be 2 cubed to the 400. Again, using the rules of indices, that's 2 to the 3 times 400, which is 1200. So I've got 2 to the 1600 over 2 to the 1200, and so I subtract those powers. 1600 minus 1200 is 400, so I'm left with 2 to the 400, and so the answer here is E. So in this question we need to take a certain number of 85p stamps and a certain number of 66p stamps and get a whole number of pounds, i.e. a multiple of 100 pence. So we could write down an equation here that 85x plus 66y is equal to 100z perhaps, where x is the number of 85p stamps, y is the number of 66p stamps, and z is the number of pounds that we've spent in total. Now, we are helped a lot here by the answers not being too large, and I'll show you what I mean by this. Because if you look at this, we can kind of see that x has to be an even number for this to work. That sort of jumps out at us a little bit perhaps, because I've got an even number here, plus this is an even number here. So the only way for this to work is for x to be even, right? So I might have x equals 2, x equals 4, x equals 6. Notice it says we have to buy at least one of each type of stamp, so I can't have 0. So x might be 2, 4, 6, etc., right? Once I notice that, you might also notice that 185 have a factor of 5 in common, so they're both multiples of 5. So for the only way for this to work would be for 66y to be a multiple of 5 as well. So I have to have like y equals 5, 10, 15, etc., right? X equals 2, 4, or 6. And now when we look at the options, the only way to make this work is for C7 to be the answer to this question, and for us to have x equals 2 and y equals 5, and nothing else is going to work there. If you wanted to give a slightly more formal written argument for that, perhaps because you're doing a similar question in an Olympiad paper, we can write that down slightly more formally. And this method does come up a lot, so it's worth noting this rather than necessarily just doing it my slightly cheating way there. Well, it's not a cheating way, but my slightly abbreviated way, I should say. I could write this down by saying, well, this means 66y is equal to 100 z minus 85x, and then I've got 66y is 5 lots of 20z minus 17 then. And then what I say is, well, look, I've got a factor of 5 on the right hand side here, but 66 is not a multiple of 5, and you might say, so 5 and 66 are co-prime or something, but this means that y is a multiple of 5, and I can do the same thing by rearranging the original equation as 85x is 100 z minus 66y, and then factorizing out a 2, so I get 2 lots of 50z minus 33y. Again, 85 is not a multiple of 2, but there's a factor of 2 on this side, so there must be one on this side as well, because everything we're dealing with here is a whole number, right? X and y whole numbers, and z. So this tells me that x is a multiple of 2, or x is even. Anyway, we're going to get to the same conclusion, that the answer to this question is 7, and you can double check if you want to and work out what 2 times 85 plus 5 times 66 is, and see it is a whole number of pounds, and this argument shows there's nothing smaller that works. So we've made a bigger picture here. We've got this hexagon that's got an area of 216, and this is one of those questions. This could be in even the Junior Maths Challenge. In a way, they ask questions like this sometimes, perhaps slightly simpler versions, but it's one of those ones where we need to add some extra lines to the diagram and split this shape into some equal shapes. Now, a hexagon always can be split into 6 equilateral triangles, and so this is fine for how I'm going to split these up. You might go further, right? And let me just say what I mean here. You might also want to add these lines in, and then you really can see, I think, quite clearly that all of the triangles that you end up with have exactly the same area. Like, all of these smaller triangles are clearly congruent to each other now. But actually, even without those, right, I can say, well, okay, I could just look at this one, for example, and say, well, these two have the same area as this one, so my divisions here are fine, and I can just count up how many there are in total here. I've got 6 in the shaded part here. I've got another 6 going around here, which is 12. Then I've got another 6 going around here, so there are 18 sections here, and the shaded area is 6 of those, so I need 6 over 18, or 1/3 of the whole shape exactly, which is shaded here. So 1/3 of 216 is 72. You can just do the division there. 216, of course, is 6 cubed as well. So the answer I end up with here is 6 squared times 2. 36 times 2 is 72. Lots of ways of just doing the calculation. Just divide it by 3, making it more complicated than it needs to be, perhaps. However you do it, we need 1/3 of the total area, which is 72. The wording might make this slightly confusing here, but really it's just a question about speed, distance, and time here. So we've got that speed, of course, is equal to distance over time, and here we want the distance, which is a light nanosecond, so we can rearrange this as distance equals speed times time, or perhaps you just remember that version as well. So the speed we've got here is the speed of light, 3 times 10 to the 8 meters per second, and the time is 1 nanosecond, a light nanosecond. So we've got 1 billionth of a second is the unit of time there. A billionth is 10 to the minus 9, so that's times 10 to the minus 9. So I'm going to get 3 times 10 to the minus 1 here, which is equal to 0.3. Then we just check the units that we're working in here. We've got meters and seconds, and this was in seconds as well, so that's all fine. So this is going to be in meters. 0.3 meters, of course, is equal to 30 centimeters, and so the answer here is B. A little bit of algebra in this question. So we multiply both sides by the denominator here, and we get 1 plus 2x plus 3x squared is equal to 3 times 3 plus 2x plus x squared. Then multiplying out the right hand side, we get 9 plus 6x plus 3x squared. And so actually this isn't as bad as it looks at all. The 3x squareds we can subtract from both sides here, and then if I subtract 9 from both sides, I get minus 8 here, and subtract 2x from both sides, and that gives me 4x. So I get x equals minus 8 divided by 4, which is minus 2, and the answer here is D minus 2. And we can, if you want, double check the answer by substituting it back in at the end if you're worried about any of the steps. But again, we've got a multiple choice answer here. That must be the correct solution, and we can really leave it at that for the challenge. In this question, we've got this number triangle, and it says each disk is to be filled with a positive integer. Each disk in the top or middle row contains the number which is the product of the two numbers immediately below it. So, for example, if I just labelled the other values on the bottom row here, let's call them x and y, then the one above the x and the n will be x times n, or n times x, let's write nx, and the one above the n and the y will be ny. And so what we've got is that n times x multiplied by n times y will give us 2022. I could write that as n squared xy is 2022. Now I always recommend going into maths challenges knowing the prime factorizations of the current year, maybe the years nearby as well, but if you don't know it, you can work it out pretty quickly here. 2022 I could split into 2 and 1011. The sum of the digits of 1011 is a multiple of 3. In fact, it is 3, so we know it's 3 times something, and you can check fairly easily it's 3 times 337. If you hadn't thought about this in advance, you might then wonder if 337 is prime. In fact, it is prime. So the important point here is that there can't be any square factors apart from 1, right? Because 2022 is 1 times 2 times 3 times 337. For a square number to be a factor, I'd have to have something at least squared inside the prime factorization. So it must be here that the n in this factorization is 1, and then there are different choices for x and y, but we must have n equals 1 because that will end up as a square factor on the top row, and 1 is the only square factor. Hopefully when you look at this, the difference of two squares jumps at you straight away. If not, you might want to go for gold in maths challenges, age 16 to 18. I've put a whole section on difference of two squares in there because it comes up so often in these challenges. So the difference of two squares, as a reminder, is this form that x minus y times x plus y always gives us x squared minus y squared. So in this example, clearly I've got x is 666, 6666. Got to be very careful about the number of digits in these, and y I would take as 333, 3333. So this difference 666, I won't keep saying it, I think I'll just write it down, but all the 6's minus squared minus all the 3 squared is going to be the sum of those numbers, so those added together and then multiplied by the difference of them. So again, if you're doing this, you obviously don't need to write down all of the working. It's just a multiple choice test. I'm just doing it to try to be clear here. So when I add them together, I get a number that has 7 9s, and when I subtract them, I get a number that has 7 3s. And now to work out this product, well, I suppose the easiest way is just to think of this as saying, well, it's 1 with 7 zeros, that's only 6 zeros, 1 with 7 zeros times the 3's with there, minus just a number that has 7 3's in it. It's not too hard to work this out. I've just got to take this number here and add 7 zeros, and then subtract this number, and now we can just do the subtraction. So I've got 10 minus 3 is 7. There's going to be lots of carrying going on here, so I'm going to take all of these to be 9s effectively all the way back to this point, and then this one will become a 2, and so now I can just do 9 minus 3 is 6 for all of these, and then I'm just left with 2 and then 6 3s. So that would be the answer to this question, and I just want to work out the digit sum now. Well, I can see there's 3 3s at the start, so there's 6 of those. That will give me 18. I've got a 2, and then I've got 6 6s here, so that's 36, and a 7. And if I add all those together, 18 plus 2 is 20, plus 36 is 56, plus 7 gives me 63. And so the answer here is E, 63. So we've got 3 rugs with combined area of 90 meters squared, and I've just represented them by this Venn diagram. So each circle will be one of the rugs. Of course, the rugs may not be circular, but this representation will allow us to solve the problem. So when they're laid down to cover completely a floor of area 60 meters squared, so in total the area is going to be 60 meters squared, the area covered by 2 layers of rugs is going to be 12 meters squared. So these parts here will be covering, will have 2 layers. The central part will have 3 layers, and the other parts will just have 1 layer of rug. So let's just label all of these regions. Let me call the ones A, B, and C that have just 1 layer, and then D, E, and F for the ones that have 2 layers, and G for the one that has 3 layers. And so what we know is that when I add all of these together, A plus B plus C plus D plus E plus F plus G, that the total area covered is 60 meters squared. But the total area of the rugs is 90 meters squared, right? So to get the first rug, I'd add A, D, E, and G together. The second one, B, E, G, and F, and the third one, D, C, F, and G. So effectively, I would be counting the parts that have 1 layer once. The D, E, and F are each in 2 rugs, so I would get 2 lots of D, E, and F, and then G would be counted 3 times because it's counted on all 3 rugs, and that would give us a total of 90. Now we're told here that the area covered by 2 layers of rugs is 12, so that's D plus E plus F, which would be exactly 12. So I could actually just replace the D, E, and F here with 12. So that would give me a 12 on the top here, and a 24 in this one because there were 2 lots there. So the first equation becomes A plus B plus C plus G is equal to 48, and the second equation becomes A plus B plus C plus 3G is equal to 90 minus 24, which is 66. Now if I subtract this equation from this one, then I'm just left with 2G on the left hand side and 18 on the right hand side, and so that must mean that G is equal to 9, and that's the answer to the question then, 9 meters squared, because that's exactly the area of the floor covered by 3 layers of rug. I've just made a slightly bigger copy of the picture for this question, and if you read the information, it basically tells you that these smaller squares, each smaller square is placed along the side of the larger square so that they're in the ratio of 1 to 2 like this, and it'll be the same, you know, from the middle square going down to the smaller square as well. But let's just focus on the large square to the middle square. So this length would also, if this is 1 and 2, this would also be 1 and 2. And so looking at this triangle, we can apply Pythagoras theorem and say square root of 1 squared plus 2 squared is the square root of 5. And then that gives us a length scale factor that takes us from the large square to the middle square of root 5 over 9, right? So we can see, so root 5 over 9, root 5 over 3. Getting ahead of myself there. Root 5 is the length of the middle square, 3 is the length of the large square. They're similar shapes because they're both squares, so there's a length scale factor of root 5 over 3, and that means that there's an area scale factor of the length scale factor squared, so root 5 over 3 squared, which is 5 over 9. So the area of the middle square is 5/9 of the area of the larger square. But then once we've done that, it's exactly the same argument to go from the middle square to the inside square because it's the same proportions, right? It's still 1 to 2, I'd make exactly the same argument. So the area scale factor to go from the middle square to the inside square is also 5/9. So the small square is 5/9 of the middle square is 5/9 of the large square. So the small square is 5/9 times 5/9, or 25/81, of the area of the large square, and so the answer to this question is A, 25/81. So in this question we've got the hare and the tortoise racing over 100 meters. They're both having constant speeds, and so let's just map out that 100-meter race starting at the beginning and going to the end here at 100 meters. And when the hare gets to the finish line, it's 75 meters in front of the tortoise, so that means the tortoise is back here at the 25-meter line when the hare is here at 100. The hare now turns around, goes in this direction, the tortoise continues in this direction, and we want to know where they meet. Well, the fact that the hare got to the finish line when the tortoise was only a quarter of the way means that the hare's speed must have been 4 times the tortoise's speed, because he's travelled 4 times the distance in the same amount of time. We're told their constant speed as well here, so it really is their speed, not just their average speed. So those speeds are going to stay the same when they turn around. So if the tortoise is going at a speed v, the hare is going at a speed 4v. So in total, the distance that they're going to travel in a unit of time is like 5v, and the hare is going to do 4v of that, and the tortoise is going to do v of that, right? If one of them's going at 1 meter per second, the other one's going at 4 meters per second, then in a second one of them will travel 1 meter and the other one will travel 4 meters. So really it's just a question of splitting this distance up in the ratio 1:4 to know how much distance, to know where they meet, because we're really thinking that they are just covering this distance between them. It's almost like some work they've got to do together, and the hare is doing 4 times as much work as the tortoise, if you like. So there's 75 meters here, so the problem really is just to split 75 meters in the ratio of 1:4, 5 parts of that ratio, so 1 part is 15, so it's 15 to 60, so that means that they're going to meet here at the 40 meter mark, when there's 15 meters covered here and 60 meters here, so that's 60 meters from the end of the race, and so the answer here is B, 60. There are often different techniques for these sorts of problems, but one thing you should always be doing for these kind of questions is just saying, can you find some reasonably easy values that you can check against these curves? So I need the square root of x plus the square root of y equals 1, so I need to find some pairs of values x and y that satisfy this equation, and then they will be on the graph. And the most obvious ones, I think, are to say the square root of 0 plus the square root of 1 is 1, and similarly, of course, the square root of 1 plus the square root of 0 is 1. So that means that the points 1, 0 and 0, 1, let me write it the right way around, 0, 1 here, and 1, 0 will lie on the curve. So we can rule out D immediately, because that one goes to the origin, but it doesn't go through any other axis points. And it also means that when I look at these graphs, if they're going to be the correct one, they have to have the values of 1 at the points where they intersect here. Now, really what we want to do now is just to find another point that works, and I think after playing around with it, the one that a lot of people will find here is to think, well, I could try and do a half plus a half equals 1, and I know that a half squared is a quarter, so actually that would correspond to the square root of a quarter plus the square root of a quarter is 1, so I get another point on the curve here, 1 quarter, 1 quarter. So actually we need, we can then see it must be B here, because, like, you know, a half is going to be somewhere like this, isn't it, along this line that goes between 1 and 1. That point here is going to be a half, so I need something that's further down this way, whereas so this one, it's not going to work. This one is clearly on that line. This one, it would go in the wrong direction. So just from that point alone, we can see that if one of these is going to be the curve root x plus root y is 1, then it must be B. With the information that, as I've done it, I don't know for sure, but because I would have to think more deeply about what all the other points are. But if it's going to be one of these answers, then it must be B. Okay, so we want to find the area of this shape that's been cut from a regular octagon. So you might start by just adding the sides onto this shape that make it into that regular octagon with side length 1, and I know that all of these side lengths then are 1 all the way around. And it's natural now to also, I think, consider this as a square. So if I just add these, extend these sides so that I get something that looks a bit like a square. I'll do a slightly better job than that of drawing these lines, but it's going to be a little bit rough. So we get something like this. Because now, immediately, I've got a way of solving this problem, right? I can just work out the side length of the square, and I can work out its area, and then I can just subtract these pieces that are all shapes that we should be able to work out the lengths of here. So by Pythagoras, right, I've got, if I want this little length here, let's call it x, right? I've got x squared plus x squared is is equal to 1 squared, so I've got 2x squared equals 1, or x squared is a half, so so that means then that x is equal to 1 over root 2, or you could write that if you want to as root 2 over 2, multiplying top and bottom by the square root of 2. I think I might just leave it as 1 over root 2 for now, or shall I? No, I'll write it as root 2 over 2. It's a simpler form, so because it's got a rational denominator. So I've got that there, and that would also be this side as well, right? So I know now that the side length of the square is 1 plus 2 lots of root 2 over 2, so that's just 1 plus root 2. So the area of the square is 1 plus root 2 squared, and I could multiply that out. 1 plus root 2, 1 plus root 2. So that gives me 1 plus root 2 squared, which is 2, plus 2 lots of root 2, so I get 3 plus 2 root 2 for the area of the square then. Now I've just got to work out the area of these different triangles, so let's start with this corner one, right? That's the easiest one based on what we've got here. So the area of this is just half base times height, right? It's going to be a half times root 2 over 2 times root 2 over 2. So I've got a 2 times root 2 on the top, so that's a factor of 2 that cancels with one of these, and then I've got an area of a quarter. So there are 4 of those, so I need to do 4 times 1 quarter, which is equal to 1 for the total of those 4 right angle triangles areas. And then I've just got to think about this this final equilateral triangle here. So what have I got? I've got a length of 1 along here, because I know that this length is also 1, and then I know that this length here is a half. So if I want to get this height, I could do h squared plus a half squared equals 1 squared again. So I'm going to have that the height here is 1 minus a half squared, or 1 minus a quarter, which is 3 quarters. So the height here is root 3 over 2. Some other ways you might get there quickly if you're familiar with equilateral triangles, quite a useful thing to be able to do quickly. But anyway, the area of the equilateral triangle then is just a half base times height, and the base is 1, so a half times 1 times root 3 over 2, so I get root 3 over 4 here. And again, there are 4 of those, so I need to do 4 times root 3 over 4, which is just root 3. So that gives us that the shaded area is the area of the square, which was 3 plus 2 root 2. Then I need to subtract 1 for the right angle triangles, and subtract root 3 for the equilateral triangles. So 3 minus 1 is 2, so I'm left with 2 plus 2 root 2 minus root 3. Then I just scan through the answers and hope it's one of them. No need to do any more manipulation here, because that is one of the answers, and it is B. Slightly sneaky question here, because it looks a bit like some problems where you end up effectively trying to write everything as 3 to the power of something, and then doing some simplification, but that argument doesn't work so well here. What we really want to do is to see these just as simultaneous equations in 3 to the x and 3 to the y. So for example, we could just say, let's let a be 3 to the x, and then let's let b be 3 to the y. And then you see, if we do 3 times a, that's 3 times 3 to the x, which is 3 to the x plus 1, and 3b is 3 times 3 to the y, that's 3 to the y plus 1. So I can actually write this first equation. 3 to the x is a, 3 to the y plus 1 is 3b, that's equal to 5 root 3. And the second equation, you can do the same thing then. 3 to the x plus 1 is 3a, 3 to the y is b, and I add those together, I get 3 root 3. So I've just got a pair of simultaneous equations for a and b. And you can use whatever method you want here now. You could find a and b and then work out 3 to the x plus 3 to the y. But if you're smart here, you can really save yourself a lot of work. Because what are we looking for? We want 3 to the x plus 3 to the y. Well, that's just a plus b. We've got a nice bit of symmetry here in these equations. So if I just add these equations together, I get 4a plus 4b equals 8 root 3. And then dividing by 4, I get straight to a plus b equals 2 root 3 without ever having to work out the values of a and b themselves. And of course then a is 3 to the x, b is 3 to the y, so I've got 3 to the x plus 3 to the y equals 2 root 3, and the answer here is B. I'm going to do this question in 2 ways. I think there's an algebraic way and a faster graphical method, but that one perhaps requires a bit more intuition. I think my first instinct with this question was to see some difference of two squaresy things around in here and say, well, okay, if I take the second equation away from the first, I get x squared minus y squared minus x in brackets. That's equal to 2022 minus 2022, which is 0. And just rearranging the left hand side here, okay, I see a difference of two squares. I've got x squared minus y squared, and then I've got a plus x minus y. So some nice factorization looks possible here. So this gives me x plus y times x minus y plus x minus y is 0, and I can pull the x minus y in here as well, and this gives me x plus y plus 1 times x minus y equals 0, and then we get either x plus y is plus 1 is 0, so that would be x plus y is minus 1, or I get x minus y is 0, so or x equals y. And you might be tempted at this point to say, okay, well, it looks like the answer is A, infinitely many, but that would be wrong. And there's a subtlety here about implication arrows in simultaneous equations and other algebraic arguments, right? You don't always think about it as often as you should with simultaneous equations, but the first line here doesn't actually go in both directions, right? It only goes forward. So yeah, if these two equations are true, then this one is true, but if this equation is true, then the first two are not necessarily. So once I've got my answer at the end here, and I suppose the other steps here, I guess, are if and only if statements, so I'm okay all the way down here. But to go back to the original equations, I need to do a little bit more. But it's certainly the case, based on this argument, that anything that satisfies these original equations will also satisfy these ones, so I can just narrow my search to these cases. So if we think about let's think about the first case. Let's do x equals y first because it's slightly easier. Right, then both equations become x squared minus x equals 2022, whether you put x equals y in here or here. Now, this is x squared minus x minus 2022 is 0, and if you've done the discriminant of a quadratic equation, you will know that this has two roots, right? Because I can work out b squared minus 4ac here. This is the quadratic equation in the form ax squared plus bx plus c equals 0, so b squared minus 4ac here will be minus 1 squared minus 4 times 1 times minus 2022, so certainly greater than 0 here, and that means that I do get two values of x that work from that equation. And then if you do the same thing with case b, right, let's call this one b and this one a. Right, well this time I'm going to do something like putting in y equals minus 1 minus x. Let's substitute that in here, and I get x squared minus minus 1 minus x equals 2022. So that's x squared plus x plus 1 minus 2022, so minus 2021 is 0. And again, we're going to see that b squared minus 4ac is equal to 1 squared minus 4 times 1 times minus 2021, but all I really care about is that's greater than 0. So I am going to get two roots out of each of these, and these roots really will then satisfy these equations when paired with their equivalent values of y. You can check that actually substituting into this equation in case b gives you exactly the same quadratic equation as well if you want to. So that's one way of doing this problem, and the second way would be much easier in some ways, which is just to think about the graphs of these two equations, right? So if I take the first equation there, so we've got x squared minus y equals 2022, I could write that as y equals x squared minus 2022, and if I now draw the axes on here, well, y equals x squared is somewhere here, isn't it, going through exactly the origin, so this graph is going to look something like this. I'm doing it roughly, it should be symmetric obviously. Now if I take the other equation, that one would be y squared minus x equals 2022, then I can write that one as x equals y squared minus 2022. So x equals y squared is like y equals x squared, but with the roles of x and y reversed, so it's the parabola on its side, and then if I say, well, okay, the x coordinates are not equal to y squared, but y squared minus 2022, that's going to shift it to the left by 2022. So that graph is going to be somewhere over here, and then we see that we do get these 4 intersection points corresponding to the 4 solutions that we found before. So you may be able to get there intuitively from those graphs of those parabolas, but I think probably most people will end up doing something a bit more algebraic, and very hard not to jump to the conclusion maybe that there are infinitely many solutions here, that you do actually have to go back and investigate them there. So there's something really deep going on here, by the way. If you haven't thought about this before, you can really think about that think about that very carefully. When you have linear simultaneous equations, this problem doesn't come up, right? So it's only when we've got these ones that are not just linear equations that we really have to think about this very carefully. Developing intuition about where to put extra lines on diagrams is super useful for the math challenges. Here we've got a circle of radius 10, and I clearly need to add some extra lines here to start working on this problem. Now, you might think, I've got to put a radius somewhere. I could put it all the way down here, I could put it anywhere else. This is not a terrible place to think about, but a much better place is actually here, because I've got this really interesting point, which is where the square then intersects with the circle again. If I add that line on and another line down here, then I can really make some progress in this problem. So I want the area of the square, so really finding the side length of the square is what we're interested in here. And so let's just say that half of the side length of the square here is x, and then the full side length of the square would be 2x, right? So that's just the length going out here. Now, what I want to notice next is that, well, this length here is also x, and this triangle here is isosceles, right? Because I'm splitting this right angle exactly in half at the top here. So I've got a 45-degree angle here, 45-degree angle here, and a right angle here. So I've got an isosceles triangle at the top of the diagram there, and that means that this length here is also x. And of course, we know that the radius of the circle is 10. We're told that in the question, right? So we've got this triangle, which is a right-angled triangle. It's got height 3x here, base x, and the hypotenuse is 10. So we can apply Pythagoras' theorem, doing so very carefully. X squared plus 3x all squared is 10 squared, so that's x squared plus 9x squared is 100. So we've got 10x squared is 100, or x squared equals 10. And the answer to the question is the area of the square, which would be 2x all squared, right? So that would be 4x squared, and x squared is 10, so 4x squared is 40. So the answer to the problem is D. This question, we've got this logo formed with 2 straight edges at the sides and then semicircular parts, so smaller semicircles here, larger semicircles around here, and we want to find the area of the logo given that the straight edges have length 2 and the small semicircles diameters are 2 as well. The maths in this question isn't actually all that hard, but seeing how to add and subtract the areas is quite tricky, I think, and it's one of those ones that once you've seen it, it appears very easy. But what I do in this sort of situation, if I can't see immediately the argument I meant to make, is just to start adding on some of these lines so I can really see the shapes, right? So I'm just going to add in some lines for these semicircles. I'm going to add some lines along here as well so I can see really clearly now these other semicircles and start labeling things, right? So I've got a length of 2 here, and a length of 2 here is what's given in the question, the length of the straight edge and the length of the smaller semicircle. Okay, I immediately see a right angle triangle here that I want to apply Pythagoras to, so I've got the square root of 2 squared plus 2 squared, or the square root of 8, which is 2 root 2. Very good just to know that the scale factor is root 2 from a right angled isosceles triangle to its hypotenuse as well. That comes up often enough, you might want to just memorize that for maths challenges. So at this point I see, okay, well I can work out now the area of the large semicircle if I want to, and the area of the small semicircle, and it's just like, how do they fit together to make this area, right? So I'm also going to kind of ignore the bottom half because I know it's just a copy of the top half. I'm looking at this, I can see, well, okay, I've got a triangle here and a large semicircle. If I put those together, I get that shape there. And then what I want to do is just to subtract this small semicircle from it, and it will leave me with the shaded area here. Okay, so that's what we're going to do. So the area of the large semicircle, right, it's going to be a half of pi r squared, where the radius here is half of this diameter, so a half of 2 root 2 is just root 2, so half pi root 2 squared, so that's pi times 2 over 2, so that's just got area pi, right? The small semicircle, well, the radius is 1, so a half of pi times 1 squared this time, so that's pi over 2, or half pi. And the triangle, well, half base times height on the triangle is just a half times 2 times 2, so that has area of 2, right? So the area that we're looking for, right, this, at least of this top part, right, is just going to be the area of the triangle plus the area of the large semicircle minus the area of the small semicircle. And overall I know I want 2 of those because I want to count the bottom half as well, so I need to double this at some point. Right, so I've got 4 plus 2 pi minus pi, and that gives me then 4 plus pi, and so the area that we're looking for is 4 plus pi, which is D. This is a very tough question. We want to find how many pairs of integers satisfy this equation with lots of square roots all over the place. So we're going to be doing a lot of squaring in this question. Definitely need to square both sides of the equation to begin with here, and when we do square, we remember that we will have to come back later and make sure that we do have valid solutions to the equation, because squaring can introduce additional solutions that we don't want. But to begin with, let's just square both sides and get x minus the square root of x plus 23 is equal to 2 root 2 minus y all squared, and then just squaring this by multiplying out the brackets. 2 root 2 minus y times 2 root 2 minus y. 2 root 2 squared is 8, so I've got 8 plus y squared minus 4 root 2 times y. If I just rearrange things a little bit here, we would get the square root of x plus 23 is going to be 4 root 2 times y plus y squared plus 8 minus x. And now at this point we think about the other important thing of this question, which is that we're looking for integer solutions only here, right? So in particular this expression here, y squared plus 8 minus x, must be an integer because x and y are both integers, and let's just call it n, right? I'm going to call n y squared plus 8 minus x just so I don't have to write it out as much. Okay, what we'll do then is square both sides of this equation again, right? So I've got root x plus 23 is 4 root 2y plus n. Now squaring both sides of the equation gives me x plus 23 equals now 4 root 2 squared is 32, 16 times 2, so that's 32y squared. I'm going to get 8 root 2 times n times y plus n squared. Again, I need this equation to be, it's going to involve integers, right? X and y are integers. So I've got integer term, integer term, integer term, and so this term is going to be awkward, right? It's got a root 2 in it, so for this to make sense that I've got integer equals integer, the only way for us to make sense of that is going to be if that term here, the 8 root 2 n times y is equal to 0. So for this to work, I must have 8 root 2 times n times y equals 0, that term, and that means that either n is 0 or y is 0, because clearly 8 root 2 is not 0. And let's just think about the different cases here, right? Suppose y was 0, then we could go back to this equation here, and if y is 0, I'll just be left with x plus 23 is equal to 0 plus 0 plus n squared, but n is y squared plus 8 minus x, so y is 0, so that's just going to be 8 minus x squared here, and if you multiply that out, x plus 23 is equal to 64 plus x squared minus 16x, so I get 0 equals x squared here minus 17x and plus 41. Using the quadratic formula, that gives me x equals 17 plus or minus the square root of 17 squared minus 4 times 4ac, so 4 times 1 times 41 all over 2, and you can check just by working out this number here that this doesn't give you a square number, so I don't end up with an integer solution here. So actually this whole case does just not work at all. So we've ruled out this case, and let's think about the case then where n equals 0 instead, and going back to that same equation here, that's going to give me x plus 23 equals 32y squared. But of course, if n is 0, then this expression here is 0, so I have y squared is equal to x minus 8, so I get x plus 23 equals 32 times x minus 8, or x plus 23 equals 32x minus 256. That simplifies to 31x equals 289, and 289 is 9 times 31, so that gives me x equals 9. And if I then go here, I say, well, okay, if x is 9, that gives me y squared is 1, so this goes with y equals plus or minus 1. So it maybe looks like there are 2 roots here. 2 is not an option, and of course we remember at this point that we've squared along the way here, so we've introduced some solutions that aren't really solutions. And you can go back and check that you know, when you put x equals 9 in here, you do get 2 root 2 minus 1, so it's the x equals 9, y equals plus 1 solution that works. And if you think about it, okay, you should check that that does actually work when you know, maybe by squaring 2 root 2 minus 1 and checking you get what you end up with on the left hand side here. But if you think about what is going on here, right? Well, if you put a value of x in here, I can certainly only get one possible value on the right hand side here. This means the positive square root, this sign to the positive square root of x minus the positive square root of x plus 23. So I can only get one answer here on the right hand side, and certainly the answer is no more. So the answer to this question, once you've checked it all carefully, is B, 1. But as I say, I think a very hard question here, lots of places you can get stuck, and you know, you really do need to go back and do that last step that I haven't filled out here, which is just checking the solutions at the end. In this question, we've got these 3 squares whose areas are given, and we want to work out the area of the overall triangle. Now, I've started here by just getting a bigger version of the picture and decluttering it a little bit by getting rid of all of the letters. And drawing a big diagram like this, and perhaps a slightly simplified one, is a very good way to start. And you've got lots of rough paper in the Senior Maths Challenge, so you can always draw your own diagram like this if you think it's more useful. Let's think about the side lengths of these squares to begin with. So the square of area 10 obviously has side length root 10. For root 40, that's root 4 times root 10, which is 2 root 10. So the side length of this one will be 2 root 10. And for root 90, that's root 9 times root 10. So the side length there will be 3 root 10. Being fluent in thirds essential for the Senior Maths Challenge. So I can start getting some of the areas that we're looking for. You know, I'm just going to try and get all of these individual triangles and add them all together, basically, right? So, you know, I've got a length here which is root 10, and then well, this is root 10 as well, but the total of this square is 3 root 10. So this bit here must be 2 root 10. So this triangle here will just have area half times root 10 times 2 root 10. So that's just root 10 times root 10, which is 10. So I've got an area for that triangle of 10. Now, we can also see that this triangle and this triangle are similar, right? And, you know, for this smaller one here, let me just draw a slightly bigger version of it here. This is meant to be this little triangle here, right? It's got root 10 as its height. Actually, let me make sure that's still on the page. So that's got root 10 here. And the base is going to be in the same ratio as this one is, right? 2 root 10 to root 10. So this one's going to be a half root 10. So the area of this one is a half root 10 times root 10 times a half. So that will be a quarter of 10, which is 2.5. You could also use area scale factors there and just say that you know that the length scale factors are 2, and so the area scale factor is 4, and get that the area here is 10 divided by 4, which is 2.5. Right, I'm going to leave this one and come back to this in a second. I'm going to go for this triangle here next, right? And again, I know this side is 2 root 10, so this is 2 root 10, so this bit here must be root 10. So again, I've got exactly an identical triangle to this one. Half root 10 times 2 root 10 gives me an area of 10, and this time that scale factor method actually goes the other way, right? I'm looking for this triangle now, and it's similar to this one. Its length is twice as big, so its area is going to be 4 times as big, and I can just say that the area of that triangle is 40. Now the tricky bit here is getting this final triangle, and to do that I'm going to make a line here. So I've got these 3 triangles being similar and these 3 triangles being similar. And that's useful because let's say I just call this base x. Well, I know the ratio of the sides in these similar triangles is 2 from the base and the height here, so this one must be 2x, but I also know that ratio is true over here, right? I double this one to get this one, I double this one to get this one, so I must double this one to get this one, so this distance here would be 4x, right? So I actually know that 4x plus x, which is 5x, that must be the square root of 90, or 3 root 10 there, okay, because that's the side length of that square. And I also know that I want to find the area of this triangle, so that's a half times 5x times 2x, so that's 5x squared. Okay, so actually 5x is 3 root 10, but that's the same as saying 25x squared is equal to 90. That's the area of this square, which is 5x times 5x, or 25x squared. So I want the area of this triangle, which is 5x squared. I've got 25x squared, so I can just divide both sides by 5 here and get 5x squared equals 18, and that will be the area of this triangle. That's these sort of two combined, if you like. For an alternative way to get the area of the final triangle here, we could also actually call this length x and say I've got a right angle triangle here, and note that this triangle is also similar to all of the other ones because it's got a right angle, you know, it's like it's got this angle and this angle, and it's got a right angle as well. Okay, it's a slightly different orientation to these ones, but they are still similar. So this would be x and 2x, and this would be the square root of 90, so I'd have x squared plus 2x squared is equal to root 90 squared, sorry, with 2x in brackets there, so that's 5x squared equals 90, and I would get that x squared equals 18, and x squared would be the area of this triangle, because this is now the base and this is the height, and the area would be a half times x times 2x, which would be x squared, so that area is 18, just as we found it before. So the total area here, all I've got to do now is to add all of these together, so I've got 2.5 plus 10 plus 18 plus 10 plus 40 for all of the ones that I've worked out there, and then I've got plus 10 plus 90 plus 40 for the squares that were already there, and I think I've got everything I need, and if you add all of those together you will find you get 220.5, and so the answer to this question is A. I'm going to apply a bit of a maths challenge cheat in this question. You'll see what I mean in a second. We've got these numbers x, y, p and q all integers, x and y are variable, p and q are constant and positive, related by this equation, and I want to know when y takes its maximum possible value, which expression is equal to y minus x. And the cheat here is that I might be able to get away with just using particular values of p and q. For example, if I took p equals 3 and q equals 4, if there is a solution to this in general, there will be a solution for p equals 3 and q equals 4. And for the maths challenge, I just want to double check that when I do take those values, that all of the solutions give me different options, so that when I know, oh okay, the answer is 5 or 15 or whatever it ends up being, I know that it just narrows it down to one of these options in the general case, right? So 3 times 4 minus 1 is 11. Here I've got 2 times 3, which is 6. Here I'm going to have 4 times 3, which is 12. Here I'm going to have 2 times 5, which is 10, and here I'm going to have 4 times 5, which is 20, right? So they're all different. So I know if I solve this with p equals 3, q equals 4, knowing which answer it will be gives me the answer to the problem. This isn't really a great mathematical method in general. We generally want to prove things for all values, but in the context of a maths challenge, trying to get the answer as quickly as we can, this is a great strategy. And I would encourage you, if you take this sort of method, to also go back and look and see if you can do it in general again. In fact, the general argument here isn't hugely harder, but I think it is a lot easier to see things when there aren't as many constants flying around. So I've got this equation now, xy equals px plus qy, and that for us is going to be xy equals 3x plus 4y, and I'm going to rearrange this to make y the subject of the equation, so xy minus 4y equals 3x, and then I've got y times x minus 4 equals 3x, and y equals 3x over x minus 4. Now if you've studied things like partial fractions, what I'm about to do next will be reasonably familiar, I hope. But a nice thing when we've got something linear over linear here, I can write this by, I'm going to basically take the 3 from the numerator here and write 3x minus 4, and that would give me 3x minus 12 if I multiplied it out, but I just want to have 3x, so I'm going to add that 12 back on, right? And the reason I'm doing that is because I want it to cancel out with the x minus 4 in the denominator here, right? So I can cancel the x minus 4 and get 3 plus 12 over x minus 4. And when I'm looking at this now, you see I can see our y is just the number 3 plus this fraction 12 over x minus 4. So that's a neat technique there that you can apply in general. Lots more I could say about that, but I want to stay focused on this problem. Right, so the other thing we remember is that x and y have to be integers here, right? Otherwise this could get as big as you want now, right? Y wouldn't have a maximum value. I could get x minus 4 very, very close to 0. This would get enormous. But to make this as big as possible with an integer, then I just need to make this denominator positive, but as small as possible. Okay, I can't do 0 because that would make it infinity, so I'm going to, or well, it will be undefined, I should say. So what I need to do here is I just want the x minus 4 equals 1 is going to be the best I can do. So when x equals 5, right, when x equals 5, then y is going to be 3 plus 12, which is 15, and that is going to be the largest value of y we can get in this case. Now in this case, the value of y minus x is equal to 15 minus 5, which is 10, and it was d that evaluated to 10, so that must be the answer to this question. I'll leave it for you as an exercise just to do this in general, right? You could also do this with p and q in place of 3 and 4. It doesn't actually change the structure of the argument at all here. It's just a bit more complicated to look at. So I quite like this as a little maths challenge cheat that just makes things a bit easier as we're going through and trying to find the answers, especially as we're getting towards the end of the paper here. Every little helps in terms of making it easier. So we're at question 25, a very challenging problem. As always, we've got a drinks carton and it's made of these triangles. I've got lengths 4 here and here, and then the longer sides PS, PR, QS and QR are all 10. So we want to work out the volume in centimetres cubed of the carton. And what we're going to do is split it down the middle here into two pyramids. So this triangle that I've just drawn, R to this point here, to this point here, I suppose I should give that a label. Let's call it M for the midpoint of QP. That is the base of a pyramid where Q is the vertical height. I guess if you sort of think of it on its side, maybe if I drew MQ like that, and then this is going to be the triangle out here, and this is the pyramid that I'm finding out the volume of, and the shape is made up of exactly two of those. So that wasn't the best drawing perhaps, but hopefully you can see there's a pyramid there, and the volume of a pyramid is a third times the base area times the height. So actually all I need to do here, well, the height is actually the easy part here, that's 2. I need to just work out the area of this triangle RMS. So we have if we look at this triangle at the bottom, MPS, okay, actually I will use a ruler here to make sure my triangles are just a little bit better. So I've got MPS like this. Well, that distance is going to be 2 to S here. This distance is going to be 10, and so by Pythagoras theorem here I've got the square root of 10 squared minus 2 squared. That's the square root of 96, and we can actually, let's just leave that as the square root of 96 for now, because I'm going to use that in the next calculation, right? If I look at the triangle RMS, okay, that's going to be an isosceles triangle. This is the one that we're really interested in here, and what I've got here is then that this length MS, actually let me label R, S and M here, so I'm putting a line down the middle of this triangle here. Well, MS was the square root of 96. Again, I know this is 2, and so this distance here, let's call this one N for the other midpoint, so this point N is here. So by Pythagoras theorem, again, I'm going to get that this, let's call it the height here, h squared plus 2 squared is root 96 squared, or 96, so actually h squared is 92, and h is the square root of 92 there. 92 is 4 times 23, so this is 2 times the square root of 23. So we're almost done actually now, because the area of this triangle is just a half times 2 root 23 times the height of 4, so that is 4 root 23 for the area of this triangle. And remember, I wanted to work out the volume of the pyramid, so that's going to be 1/3 times the base area, which is 4 root 23 times the height of the pyramid here, which is 2, and I've got two congruent pyramids, so there's that one and the one on the other side, so I just need to multiply this by 2 at the end as well. So I'm going to get 2 times 4 times 2, that's 16 over 3 times the square root of 23, and that gives me the answer to this question, which is A. So very well done if you got that right.